Okay, so now I want to find the Fourier transform of a very useful function in the context of derivatives. I want to find the Fourier transform of f prime. So notice I'm not doing the derivative of the Fourier transform. There's an exercise that involves that, or a homework problem that involves that, but you have to do the homework problem before you see that it involves that. Okay, but I want to take the derivative of f and find the Fourier transform of that. Okay, and I'm going to be assuming two things. I want to assume that both f and f prime are integrable, really absolutely integrable. I use those terms interchangeably. And that's just because I want the integral definition of the Fourier transform of both of these things to exist. Another thing that I'm going to use the fact that the limit as r goes to plus or minus infinity of f of r is equal to 0. Now at first this might seem obvious because I'm assuming that f is integrable. But there are functions where this limit does not exist. Okay, there are functions where this limit does not exist. Sorry, there are integrable functions where this limit does not exist. Okay, so it's not clear just because we know f is integrable that this limit exists, and if it does, whether it's equal to r. However, since f is differentiable and f prime is integrable, we can use the following fact: f of r minus f of 0 is equal to the integral x equals minus r to r, x equals 0 to minus r, f of x dx, f prime there. And I want you to use this fact here to, 1, show this limit exists, and then 2, if it exists, the integrability of f will imply that the limit is equal to 0. So that's something for you to think about on your own. Okay, but now I'm going to compute the Fourier transform of f prime. The Fourier transform of f prime of omega. Okay, I'm going to have my integral here is going to be 1 over the square root of 2 pi times the integral x equals minus infinity to positive infinity f prime of x e to the minus I omega x dx. Okay, now what I want to do is I want to try to get this in terms of the Fourier transform of f, which means I don't want there to be a derivative on the f prime. And there's one integration technique that lets you move the derivative from one function onto another function. I'll let you think about that for a minute. Pause it if you want to think about it. Okay, that integration technique is integration by parts. It's one of the most important integration techniques. So this is v prime, and this is u. And then v, if v prime is equal to f prime, this means v is equal to f. And u prime, I'm taking the derivative with respect to x. So this is minus I omega e to the minus I omega x. Okay, and then so using integration by parts, I'm going to have my 1 over the square root of 2 pi on the outside of the integral. I'm going to have my boundary terms, that's u times v. U is e to the minus I omega x, v is f of x, so this is going to be equal to f of x e to the minus I omega x, and this is x going from minus infinity to positive infinity. And then it's going to be minus the integral of v times u prime. Now u prime is minus I omega x, so the minus is canceled, and it's going to be plus I omega times the integral x equals minus infinity to positive infinity of f of x e to the minus I omega x dx. Okay, now this part right here, the boundary terms, f of x times e to the minus I omega x, going from minus infinity to positive infinity. By this fact right here, about the limit, it says this is equal to 0. And so what we're left with is I omega times 1 over the square root of 2 pi times the integral x equals minus infinity to positive infinity f of x e to the minus I omega x dx. And this is equal to I omega. Well, this right here, look, what do we have? It's 1 over the square root of 2 pi times the integral. It's the x integral going from minus infinity to positive infinity. And the thing we're integrating is f of x times e to the minus I omega x with respect to x. So this right here, this part right here is just the Fourier transform of f. So this is f hat of omega. Okay, so I'm going to record that over here. What this tells me is that the Fourier transform of f hat is equal to I omega f hat of omega. I'm about to trace all of this over here. So now what I want to do is I want to find the Fourier transform of f double prime. So in other words, I want to find the Fourier transform of the second derivative. Now I could go through this whole process again. I'd have to do integration by parts, but maybe I can use this idea. Maybe I can use what I've already figured out here. So the Fourier transform, I'm going to use fancy f notation here. The Fourier transform of f double prime of omega, well, this is equal to I omega times the Fourier transform of f prime. Because f double prime is just the derivative of the derivative. Well, the Fourier transform of f prime, I have my I omega. The Fourier transform of f prime is I omega times the Fourier transform, let me put the argument here, times the Fourier transform of f at omega. Well, this is equal to I omega squared times the Fourier transform of f. Okay, so then over here, the Fourier transform of f double hat, or sorry, not f double hat, f double prime. Notice the hat includes the double prime here, is equal to I omega times f hat of omega, sorry, I omega squared. And in general, if we take the nth derivative, if we take the Fourier transform of the nth derivative of f, it's going to be I omega to the power of n times f hat of omega. Okay. And so these are the derivatives, the Fourier transforms of the derivatives. As you can probably imagine, that's going to be important when we're solving partial differential equations.